Good morning. This video covers periodic trends. A trend is a generalization that uses patterns to explain some type of phenomena. We will use the trends to predict characteristic properties of the elements based on the number of valence electrons. This video will cover atomic radius and ionic radius, ionization energy, electron affinity, electronegativity, and metallic character. Our next trend is ionization energy, which is defined as the energy that is required to remove an electron from a gaseous atom or ion. You can notice here in this instance that the electron is being released as a product, and since it is talking about the energy that is required, it is always going to be increasing the amount of energy that is present within the atom. As you continue to take away more electrons from an atom, the amount of energy that is required to remove them will be higher. You can see that in the case of magnesium, and with magnesium you would notice that it would have 2 electrons in the first energy level, 8 electrons in the second, and then 2 electrons in the third. So you can see here that when we remove the first electron out of the third energy level, it would take 735 kilojoules per mole. The second one from the third energy level would now require 1445. That is again due to the amount of attractive forces that are acting on that last electron from the nucleus. You've minimized the amount of repulsion between the 2 electrons that are sharing the energy level, and so as a result it requires a greater amount of energy. But the one that I want you guys to really notice here is when we remove the third electron. So these would be the first 2 electrons that we would remove from the valence shell, but the third electron that would be removed would have to come from the 8 electrons in the second shell. And so as a result, you'll notice a huge jump in the amount of energy that is required, because now the number of core electrons would only be 2 that would be shielding the nucleus and the outer shell, and so you have a much stronger force of attraction, and that greater force of attraction causes a much larger amount of energy to remove the electron. So for the period trend, in general, as we go across a period from left to right, the first ionization energy will increase. Please remember this is the Z effective concept that we were discussing. As we add more electrons into that same energy level, they're getting the same amount of shielding from the core electrons, but we're also adding protons into the nucleus. So the Z effective is going to increase as we go across, and that is going to increase the force of attraction that's occurring between the nucleus and the outer shell. When we talk about the group trend, this is going to be looking at the shielding effect. And as we go down the group, because we're adding extra energy levels filled with electrons, you're going to see a greater degree of shielding. So that increase in distance, going back to Coulomb's law and that law of inverse squares, the distance is going to be increasing between the nucleus and the outer shell, and so that's going to cause a reduction in the force of attraction. So when we discuss the trends for ionization energy, the atoms that typically will have a low ionization energy tend to form cations. So that is going to be in the left-hand region and more towards the bottom on the periodic table. You have the high ionization energy elements that will tend to form anions. They're not going to want to lose electrons, they're going to want to gain them. And so those would be more found over in this area for the high ionization energy versus the low. Now, the noble gases are an exception to that because, again, they already have that completed outer shell, so they have their S&P sublevels completely filled up, so therefore they do not want to lose or gain electrons. They want to stay where they are. So they will not form anions, but all the other high ionization energy elements will. As a summary for this, again, it will we abbreviate ionization energy as IE. It is going to increase, again, going from left to right and from bottom to top for those values. The last thing that I wanted to talk about with ionization energies is when you're looking at multiple electrons that are being removed. And you'll always notice the largest jump in ionization energies when you leave the valence shell and you end up going into the core electrons to try to remove them. So the values that you're seeing here are giving you the ionization energies in terms of megajoules per mole. When we look at these, you can see the number of valence electrons that are found on the atom. That's in the second column. And you can see in the shaded region, that's where the core is. So you can notice you get large jumps going from 0.52 to 7.3, 1.76 to 14.85. You'll see the largest jump, and that'll be your way to identify where the valence electrons would be for an unknown element, is by comparing where you find the largest jumps in ionization energies. So for the carbon atom, if you look at it, it has 4 valence electrons. You can see the increase initially is pretty linear. It's going from 1.09 to 2.35 to 4.62 to 6.22, and then all of a sudden when it removes that 5th electron, now all of a sudden it jumps up to 37.8. So you have almost a little over a 600% increase in the amount of energy that's required. So let's now take a look at another set of example problems, and this time we are going to be ranking the elements for the first ionization energies according to a decrease in ionization energy. So once again, that general trend for increasing was going up and to the right. So in this case, for decreasing, we want to order them going down and to the left. So when we look at our first set here, I have krypton, helium, and argon. All three are noble gases. So I have krypton, argon, and helium. So again, with it increasing as I go up the group, I'm going to start with helium having the largest first ionization energy, and then argon, and then finally krypton would be the lowest. If I look at B, I have antimony, tellurium, and tin. So those are all elements that are in the same period. So I have these three, and again it increases as I go to the right. So tellurium would be my greatest ionization energy, and then I would have antimony next, and then tin would be my smallest. When I go to C, now I have elements that are not found in the same rows any longer or in the same columns. So we're going to do the same type of comparison. I have potassium, calcium, and rubidium. So again, I know that since my ionization energy is going to increase as I go up, I know that rubidium is going to have my lowest out of those three. So I'm going to go ahead and put that down here. And now choosing between potassium and calcium, since ionization energy is increasing as we go to the right, calcium would be a greater ionization energy than potassium is. So in this case, I would have potassium next, and I would have calcium as the highest. Okay, and our last example, I have iodine, xenon, and cesium. So in this particular instance here, again, cesium being not only further to the left and also the lowest for my energies levels here on the periodic table, being in row 6 versus row 5, I know that cesium would have the lowest first ionization energy. And then between iodine and xenon, the iodine would have a lower ionization energy than xenon because, again, Z effective is smaller, so it would have a smaller force of attraction. So xenon would require the most amount of energy to remove that first electron. Our next trend is going to be electron affinity. Electron affinity is the energy change that occurs when 1 mole of electrons is added to 1 mole of gaseous atoms or ions. Please understand this is not the opposite of ionization energy. We are creating anions this time instead of cations. It does have an equation that we can use, which would be taking any element A and reacting it with an electron and forming an anion, and then you're going to have a release in energy. A second thing that you could have equation-wise would be that atom taking in the electron, and this time having the energy being added in, and then forming the anion. Now, one of these two processes is favorable to the other, and the answer to which one is the favorable process is going back to the relationship that we've always been talking about with energy for the atoms. They always want to be as low in energy as possible. So having the energy being released, as we have in that first equation, would mean that I would have a lower energy position for the anion than I would for the one where I have the endothermic process where the energy is added in when the electron is taken in. So for this one, you would have a higher energy overall, which is not favorable. Okay. So atoms with a low electron affinity are going to tend to form cations, and atoms with a high electron affinity will tend to form anions. Now, I'm going to do another video that is going to cover a lot of the exceptions that we have. Electron affinity is probably the most irregular of all of the normal four trends that we discuss, along with ionization energies. So as we start to look at the period in the group trends, please remember that the more negative the electron affinity value is, the higher we term that electron affinity. So we're releasing more energy in the process. As we go across a period from left to right, the electron affinities are going to become more negative. Therefore, they're going to be a higher value, giving off more energy. This is due to the fact that the increase in the Z effective, adding more protons in the nucleus while keeping the core electrons the same, that is going to cause a stronger attraction for the electrons that are going to be entering the atom. We do have a problem, as I'll discuss in the next video, where the interactions that are occurring between those electron-electron repulsions can really cause some variations as we go across the group, or across period, excuse me. The group trend, in general, the electron affinity is becoming more positive or less negative as you go down a group. So as it becomes more positive or less negative, it's going to be releasing a smaller amount of energy, and so as a result you see a less advantageous position energetically speaking for those atoms. And so we'd say that the electron affinity would decrease as we go down the group. When we talk about this, again, same thing, you have Coulomb's law coming back into play for this. Further distance from the valence electrons, you get the atoms getting, or the electrons being more shielded from the nucleus as a result, and you get a smaller release of energy. So the overall trend, when we are increasing electron affinity, it is going to do the same as the ionization energy. It will increase as we go to the right and also as we go up the group. We're now going to begin to predict the patterns based off of ionization energies and electron affinities. So when we're talking about this, you're going to see a couple different terms here: reactivity or chemical activity, or you can term it as metallic character as one of the properties that we can look at. So when we first start off looking at ionization energies, your reactive nonmetals, they're going to be the substances that have high ionization energies and high negative electron affinities. The electron affinity is the more important one because, again, it's going to have that strong attraction to the electrons, and it's going to release a lot of energy when they accept the electron and become an anion. So these will be your anions, again, that negative ion that will form in your ionic compounds. For your reactive metals, they're going to be the ones that have the very low ionization energies. They may have a slightly negative or barely positive electron affinity, but because of the fact that they have this low ionization energy, that means that they will be able to lose their electrons very easily, and it will not require very much energy to do so. So these will typically form the cations for your ionic compounds. Again, that positively charged ion in the compound. Now, with these reactive metals, again, the lower the ionization energy is, you're going to have a more reactive substance. So most of these reactive metals you will never find in nature as an element. You would always find it as a compound. So these will always be found as a compound. Okay. Noble gases, because they have very high ionization energies and only slightly positive electron affinities, these typically will not tend to form cations or anions. They'll just stay alone as it is. We have formed a few compounds with noble gases. However, it requires a tremendous amount of energy to be added in, and it has to be with one of the nonmetals like fluorine or oxygen that have very, very highly negative electron affinities. All right, so the last trend that we're going to look at is electronegativity. And electronegativity is the measure of the ability of an atom in a molecule to attract an electron to itself. It was a concept that was proposed by Linus Pauling, and it basically is like a tug of war between the two atoms that are sharing an electron. Which one has that stronger force of attraction to take those shared electrons in? So when we're looking at the period trend, the more protons that the atom has, while the energy levels are the same, means that the atom can better attract the electrons. So again, having a larger Z effective value means it'll have a stronger electronegativity. The electronegativity is going to increase to the right on the periodic table. So again, if we just label that as En, and we have it increasing, it's going to increase as we go from left to right, because again, within that row, I'm increasing the protons, I'm increasing the electrons, so the Z effective is going up. Now, when we talk about the group, now we're focusing on distance. So again, think Coulomb's law, think shielding coming into play here. So with the fewer energy levels between the electrons that are being shared and the nucleus of an atom, you're going to have a stronger force of attraction. So having these smaller atoms, less energy levels filled with electrons, that is going to increase the electronegativity. So in this case, the electronegativity is going to increase as we go up the group. So again, less shielding because I have fewer energy levels in between the nucleus and the electrons that are being shared in the outer shell, and so you have a stronger force of attraction. Okay, so let's just do a quick summary of these different periodic properties. So our first one, Z effective, again, it is going to increase as we go from left to right across the periodic table. This is again due to the number of core electrons staying the same, while the protons and the electrons in the outer shell continue to increase. The Z effective from top to bottom, again, disregarding the Slater rule, we are going to have this stay the same. So have an increase in the number of protons that's proportional to the increase in the number of electrons that are in the core shells. Valence electrons stay the same, so therefore the Z effective stays the same. As far as shielding is concerned, this going from left to right, because I have the same number of energy levels being filled with electrons, the shielding will stay the same. As we go from top to bottom, the amount of shielding will increase because I am increasing my number of core electrons. As far as the electron energy level is concerned, Again, same type of concept, going from left to right. The electrons are all being added into the same energy level on the periodic table, so that would stay the same. And then going from top to bottom, the electron energy level would increase because we're adding more core electrons. So when we start to look at the different properties that we have in terms of atomic radius, going from left to right, again, that is going to cause the size of the radius to decrease, and as we go from top to bottom, it is going to cause the atomic radius to increase. For ionic radius, from left to right, again, it is going to vary as we go due to, again, the interactions that we have with the number of electrons that are found in the shells versus the protons. Think about the charge differences that we had talked about for that. From top to bottom, it will stay the same, and it will increase just like atomic radius does because we're still adding extra energy levels filled with electrons. So again, like I said, there's no set pattern going all the way across from left to right. For the ionic radius, it's going to get smaller as you go with an increase in charge, okay? And then larger with a increase in negative charge. For the ionization energy going across from left to right, this is going to increase, and from top to bottom, this will decrease for that. So again, increasing Z effective is increasing attractive forces, so it holds on to the electrons more tightly. Top to bottom, again, it's going to decrease size, distances increasing as a result. Electron affinity, you are going to have an increase in the electron affinity going from left to right. Again, the ability to attract the electrons increases with the number of protons, and then going from top to bottom, it is going to decrease as well. So you would have a larger distance going between the nucleus and the electron that's being acquired. For the electronegativity, going from left to right, again, that will increase. Extra Z effective causes stronger force of attraction. Going down the group, increasing the distance will cause a decrease in those forces of attraction. So that is going to wrap up this first video. Like I said, the next one will discuss your exceptions to the trends for ionization energies and electron affinities.